Hi everyone. In this lecture on elements of games theory, we consider decision-making procedures while accounting for probabilities of possible states of nature. But first, I'll remind you some non-probabilistic decision-making procedures. And second, the decision-making we'll consider decision-making while accounting for probabilities of possible states of nature. We call it probabilistic decision-making. I'm splitting this lecture in three parts. The first part will be explanations for beginners. The next one will be given in the next part, second part, I'll give an example and we'll call it intermediate section. And the last part of this lecture will be for advanced students. I'll consider a more advanced example of how to make decisions in conditions when we have some probabilities of different states of nature available. So let's talk about this decision analysis. Decision analysis provides us a structured way for ranking decisions options by the following order. First, we enumerate the immediate and later choices available to a decision maker. This DM abbreviation stands for decision maker. Second, we characterize all the relevant uncertainties. 3. We quantify the relative desirability of different outcomes. 4. We provide rules for ranking the decision options, thus helping the decision maker to select the best option. The best option. How do we do this? We have different approaches. First, non-probabilistic decision making, when we don't know probabilities regarding the different states of nature. Or we can switch to a probabilistic decision making procedure when we know probabilities with which the nature will turn to one of its states. In previous non-probabilistic decision-making procedure, we considered this example where we set a different pricing options regarding some software, and we had this payoff matrix for the best market conditions expected, for the mild or most probable market conditions expected, or worst market conditions expected, and different payoffs, expected payoffs depending on a pricing policy. The pricing policy is the payoff per unit unit product. So now we enumerate the choices. These are our choices, different pricing strategies of $4 per unit, $4.6 per unit, or $4.8 per unit. We can call this the first option, we can call this the second option, and we call this the third option. So we enumerate choices. Now we characterize uncertainties. Our characterization of uncertainties include best market expected for this product, mild market or most probable market expected for the product, and worst market or bad market expected for this particular product. Now we quantify relative desirability of outcomes. We quantify by setting these payoffs given every market condition, every uncertainty, and given every choice. So we get the matrix which combines our choices and our uncertainties. So we get this matrix with payoffs. Now we need to apply objective analysis to select the best option. Probabilities of various states were unknown. We figured out that at the previous lecture that we can use the maximax or risk-taker approach while maximizing the payoff, or we can take the maximin approach. We can maximize the minimum, the worst case payoff. But these strategies, non-probabilistic decision-making strategies, they work only when the probabilities of these conditions, of market conditions, are unknown. So that was the reason we call it a non-probabilistic decision making. We don't know the probability with which the market will turn to its best conditions, or market will be mild, or what's the probability that the market will turn to the worst market. We've considered this situation. Now we consider the next situation. We get additional information in form of these probabilities. We get the new information. Sometimes the probabilities, we can call them odds, of various market conditions can be assigned or evaluated. We can artificially assign some probabilities to these different market conditions, or evaluate using the market surveys, and there are different methods to how to obtain these probabilities. But anyway, we're given these probabilities. The best market condition will appear with probability of 0.5. The most probable market conditions will turn out with probability of 0.3, and the worst market conditions can be expected with probability of 0.2. Now, when we have all this new information, now which option is the best? Now we know the probabilities of different states of nature, unlike in the previous case. We know these probabilities, or we're given these probabilities. Now, how do we specify, or how do we find the best option given this new information? Formally, we can apply this maximum probability criterion. It's pretty obvious, and it's the simplest approach. The simplest approach is to maximize expected payoff given maximum probability, or the odds of the nature's state. For example, we call these probabilities the odds. So we can maximize the expected payoff given the maximum probability. So we analyze these probabilities, and we obviously see that the maximum probability is for the best market conditions. So we can maximize the payoff given this maximum probability of these different states of nature, which is the best market conditions. So we maximize payoff given this particular market condition, and we see that the best option is the second option. So formally, this maximum probability criterion works like this. We maximize the payoff given that the probability of different states of nature is brought to its maximum. Here, P sub j is the probability of corresponding state of nature. Now we can illustrate this by the following. Now let's split this in several steps. We can solve this in several steps. First, we find the maximum probability of different states of nature. We analyze different states of nature. We see that maximum probability of 0.5 is assigned to the best market conditions. So P sub j 0 equals to 0.5 in our particular case. Now we maximize the payoff. Given that particular state of nature, which is the best market condition here. So we maximize the payoff, we analyze different payoffs and find the maximum given this particular state of nature. So the best option is to set payoff per unit to 4.6. So our maximum expected payoff of $24,400 will be obtained or will be received at the second decision making option, which is $4.6 per unit of the software. Now, this method has some drawbacks. Only some of the nature states take part in actual analysis and decision making. We don't analyze or we don't account for all the states of nature and payoffs given that different states of nature. And this method disregards the most part of information provided by the payoff matrix. We take only part of the payoff matrix. Now, we can solve this by maximizing the so-called expected monetary value, or EMV, of the earnings payoffs. Formally, the formula for this maximum expected monetary value looks like this. We maximize this sum. Sum runs by subscript j running from 1 to n, where j shows different states of nature. This sum runs through all the states of nature. Inside the sum, we've got these different payoffs, f sub ij times p sub j. P sub j is the probability of this particular state of nature, and f sub ij stand for payoffs given this particular state of nature, every particular state of nature. So formally, we find all these sums and then maximize over I. Now, we can illustrate this in the following example. Now let's apply this maximum expected monetary value criterion to our payoff matrix. So, the expected monetary value for every decision-making option is shown in this column. So how do we get this expected monetary value for every single decision-making option? As the formula shows us, or as the formula tells us, we multiply the corresponding payoff for this particular decision-making option times the probability of state of nature and find the sum over different states of nature. So we just take a corresponding payoff for the state of nature number 1, which is best market condition. We multiply this payoff by the probability of this particular state of nature and add the next value. We multiply this payoff by this probability plus this payoff for the most probable market conditions times the probability of this particular state of nature, which is 0.3 in our case, plus the payoff for the worst market condition, which is 0, times the probability of this particular state of nature, 0.2, and sum these products. So in total it will look like this: 24,000 times 0.5, it's here, plus 16,000 times 0.3 plus 0 times 0.2. In total, this will equal the 16,800. Now the second decision-making option will have the expected monetary value of 16,810, and the third decision-making option will have the expected monetary value of 13,040. Now, by maximizing or finding the maximum of these three expected monetary values, we obviously see that maximum expected monetary value is achieved at the second decision-making option. So, obviously, the best option is to set payoff per unit to 4.6, because it gives us the maximum expected monetary value. So this is how we analyze the payoff matrix, given that we know, or we given the probabilities of different states of nature. So, does this new criterion has some advantages? Yes, it does. It gives simple procedures for analysis and decision making, and it accounts for all the information provided by the payoff matrix. So, we finish this video at that. We'll leave it at that, and we'll proceed with the example at the intermediate level and the next video.